on. So basically, when we think about rings, and this is really the whole point of this chair structure, is that ring structures exist, and they're very important in chemistry. Even in your body, things like cholesterol have rings in them. And so to understand this, we need to go back and think about a lot about our Lewis structures and how we did Vesper and all that good stuff. So, do you remember what the bond angle is for tetrahedral? I know that that's such a weird question, but it's actually on the screen
Isn't
right
it
now.
like 100 and something?
109.5 degrees. And so that is what the ideal bond like this. Because remember, Vesper, the valence shell electron pairs, bonds and lone pairs want to maximize their distance away from each other. So basically, they want to just get as far apart as possible, right? Mm-hmm. So like if you had something with two bonds, they would be 180, and then a triangle would be 3 with 3 bonds as the trigonal planar. And so now, if I was to draw here, what if I had 3 carbons like this in a ring? What is this bond here? Any idea? It's a triangle.
Angle?
Yeah, and so what's the angle? You should know this. This is a geometry thing you learned in like 3rd grade.
90?
Nope, that's the right angle. The sum of an internal angles of a triangle should be 180. And so since they should all be the same length, you're just going to divide it by 3. So the bond angle is 60 degrees, right? So if we think about carbon in a ring like that, that angle, is that very far from our ideal angle? Yes, because it wants to be 109.5, right? So we're now making it unfavorable. Does that make sense, Mags? I see a little confusion.
Yeah, it makes sense.
Okay. So basically what happens is that when we make these rings, we run the risk of making something called torsional strain. Torsional strain is just that we're putting our bonds at such small angles that it's not ideal. Our orbitals are overlapping and it's not great. And so if someone says, why is a ring, what's happening here? So torsional strain is basically, there's all these things that can happen when we think about our strains, right? We can have angle strain and steric strain. Steric is like when they're too close to each other. Angle is when they're not there at their ideal angle. And the idea here is that when we build ring structures, all of the strain is going to pop up unless we think about it and try to fix it. So a triangle is just, a 3-membered ring is just so unstable, it's reactive because they're just too close to each other. So that's why 3-membered rings are not ideal. They exist, but they're not ideal. So when we start talking about cycloalkanes, we have these right here, and you can see 60, 90, 108, 120, 129, and 135. And so what happens is that if cycloalkanes were flat, each carbon would experience angle strain. But again, they're not flat, right? They're existing in 3D environment, so there are a little bit of turns and stuff. So what we expect, which of those rings, 3, 4, 5, 6, 7, 8, looks to be the best one based on angle strain? Which one's closest to our ideal angle?
The pentane?
Yeah, the cyclopentane looks correct, but that's only if it's in a 2D, but it's actually going to have a 3D conformation. So which one actually has the best angle is the 6-membered, because it doesn't exist as a flat piece. It's like the chair conformation that you guys are talking about, right? Yeah. And so that's why if you look at it in a 2D shape, you're like, oh, the 5-membered ring looks great. But actually, if you draw it in the correct thing, it's the 6-membered ring that actually gives you the most stable one. So cycloalkanes, and here's the combustion data for cycloalkanes. And basically, the combustion data is essentially if you were to burn it, how much energy you release per CH2 group. And so the 3-membered ring has the greatest combustion per CH2 group. If you notice, 4-member, 5-member, 6-member, and 6-member you can see is our lowest. And it crawls back up 7, 8, 9, 10, 11, 12. And then when we get to 13, it drops back down. So this is very important to talk about. When it's combustion per CH2, our cyclopropane is the highest. That's the highest rate. If you increase the carbon size, the combustion increases naturally. So basically what's going to happen is that your 4-membered ring will have more energy than the 31.5 more than 4. So like as you add carbons, the overall combustion is greater. Does that make sense? Okay. All right. And so cyclobutane is 27 per kilojoules per mole less stable than cyclohexane. Angle strain bond angles of 88 degrees, and there's slight torsional strain. And basically, if your bonds, if your orbitals, if this is your atom like this, if your orbitals line up perfectly like that, it's unstable. But if you can get them to turn away from each other, they become more stable. And that's the idea of the torsional strain.
And it's because they're farther away.
Mhm. All right. How does that sit in with you guys?
Good, because I feel like she went through this entire page in like 2 minutes, and then I was like, "Wait, what?" So like, slow down.
Do you guys have molecular kits?
Yeah.
Yeah, but I don't really know how to use them.
You pop them together and just play with them.
I have one right here.
Okay, I want you, when I start drawing something, I want you to, if you have your kit with you, I want you to build a 6-membered ring of carbon. So those are the black ones. At least they should be. Are you yelling at Zeke? Zeke, fetch me my model kit. I will only have time for one session today, like the 40-minute thing, but then I'll record whatever we don't finish and do some practice stuff later tomorrow and post it. So if you have questions, you can always send me them, and I'll address them in the PowerPoint or in the video.
Okay.
And my school has a Zoom license. I'm getting it tomorrow, so I'll be able to do longer sessions. I don't have to keep. I didn't know we had one, but we do.
Okay, I have it now.
Okay, oh, wow, there's all sorts of things wrong here. Gonna stop sharing real quick, and I'm wondering if it's just the word dealing that opened up. Yep. Okay. So basically now what we're going to talk about, I guess, all right, we're going to get into isomers at the end of this, but we'll just focus on the ring structure. All right. So basically, as I was saying, when we think about this ring structure, right, you guys, if you see it drawn on the page normally, this is the ring structure that you guys see, right? And Gwen, what's the problem with drawing my ring like that? Well, besides, I got drawn again. That's ugly. What was wrong with the way that I drew that?
Are you so? Are you? I don't know.
Well, it's the same issue that we have with Lewis-Dot diagrams and all those other things. It's 2D. It's not a correct representation. Right? And so that's really why we want to draw this, is that we've got to have the correct 3D representation for this. And so when we draw these ring structures, this is what allows us to do that. Does that make sense? Okay. So basically, at the heart, that's what we're doing here. And that's really what we have to just keep an eye on. All right. So now knowing that, we essentially now just want to go do this stuff and make sure we're doing it correctly. So in reality, our ring, have you guys built your 6-membered ring yet?
I don't really know like how.
So take a carbon and put one of the bonds, like the little plastic thing, and connect it to 2 black ones. How's it going, Max?
I got my first one.
Okay, just add 4 more, and you're going to all connect it. You're going to have to kind of twist and turn them to get it.
This is fun.
I know.
So this is where I'm about to drop some really unfortunate news
Ow.
to you guys. Is that the people that excel at organic in this section are those that can do this in their head. This is why I did really well at organic, is that I'm just really good at visualizing in 3D.
Unfortunately, I see. Yeah, you drew the ring. I was like, that's fine.
Well, if you play video games, you're actually really good at this. And the reason why is that if you play video games, you're playing them on a 2D screen, but it's in an environment that's a 3D world. So your brain translates that 2D into a 3D thing.
Does this look right?
Yeah.
I'm trying to figure out like which pieces because I've never actually.
It's the black one and the simple plastic like bar things. The black ones, it's the atoms that have 4 holes in it. Usually carbon's black in those kits.
Okay, I think I have a different kit.
It might be green. Just find one that has 4 holes.
Okay.
Did you like my old man rant that I sent you in the snap?
Oh, I haven't looked at it yet.
Okay, it's an old man rant. I'll tell it to you, both of you, since you're here. Max can hear it too. It's actually, hold on real quick. Okay, so all you're doing is connecting those things. So did you find the one with the 6 holes?
I don't think I have.
Oh, 4 holes. 4 holes.
Okay, I'm like using the
Can you hold up your kit so I can take a look?
I have this one. It was one of the options she gave us.
Yeah, I think. Oh, it's those ones. Yeah, like the little joints or the bonds, like the little clips go together, right?
Yeah, like these things.
Yep, snap them together to form a bond, to form a carbon where 2 of them come together. That's a.
Like that.
Yep. There you go.
Yeah, I was like, these do not have.
Yep. Okay. So anyway, Mag, hold up your little ring sideways. So hold it up sideways. Okay. That's not the ideal bond angle because it's not happy. So what I want you to do is to twist it. So the 2 you're holding, I want the one you're holding in your left hand to point down and the one in your other hand to point up. So just kind of twist and turn, however, so slightly.
Like that?
You want to keep them connected.
Oh. Hold on.
Oh my god! Wait.
But how do you?
Yeah, like that. Yep. So you want to get it so that the opposite side ones are pointing, one's pointing up, one's pointing down. That's yeah. So try to. That might be a little too far, but
Wait, I can try and like twist it.
Like this?
That's one of the confirmations. But you see, move your hand. It's a little bit better. Hold on. Can you turn it like this? Just rotate it so I can see. No. I'll go back a little bit. Okay, right there. You see the ones that are both pointing down?
Uh-huh.
You want one to point down and one to point up. So you want 2 carbons that are opposite to be like
This?
yeah, like that kind of. Is there 6 there?
It looks like it. If I like angle it, it looks like the.
Yeah.
Yeah, there's 6.
Yeah. Kind of. You almost got there. This is something that's done in class. I would walk around and do this for you guys. It's really hard to do.
Yeah,
Online.
especially over Zoom.
Yeah, but anywho,
Oh,
you understand though that when I turn it right, I can bend it so that I'm changing the angles.
Yeah.
And basically, it's not planar. It's actually this weird bent thing.
So when they draw a ring, it's like does not actually look like that at all. It's okay.
Yeah, correct. And so this is called the chair conformation. Basically, the chair conformation is the most stable way to make the 6-membered ring. It minimizes torsional strain, it minimizes angle strain, and it'll give it the best stability. And so this chair conformation is essentially what we try to get our molecule to look like. So we also have something called boat conformation, half boat, half chair, and those are not ideal, right? So the reason why is that once you get it out of this perfect chair conformation, you bring in torsional and angle strain, which is not great. And so essentially, when we think about our cyclo, we have to think about it in this shape like this. And so the important thing is when you draw it, if you get the model built right, once you see how to build it correctly, which you're going to have to ask someone to show you, maybe in the tutoring center or something or whatnot, I would just, what I used to do is what I've seen people do, and I recommend it, is just keep that in your bag, the 6-membered ring. You can separate it and put it in a plastic bag, but at least keep one. Yes.
I kind of
Did I get it?
I think so. Yeah, I think that looks right.
up and these.
Yeah. That's right. That's right. One goes up, comes down like that. It looks like it's alternating. So up, down as you go from carbon to carbon.
Yeah.
Yep. That's what it looks like.
Hmm.
So when it does that, it's minimizing that energy. So if you were to look down, like the perspective, like at it, like imagine this is the carbon in the front, like you're looking down the side, and then you have a carbon behind it, like that, and then you're going to go to a carbon here, like this, and then you're going to have a carbon like that. So you can imagine that if you look down and you can see one carbon going up, one carbon going down, and you can see down the other two. That's what you should look like. So if you look at it, look straight forward at one of the carbons so that you have like 1, 2, 3. There's the 4th carbon is directly behind you. So hold it up to the camera so we can look at it at the same time. So, yep. And you can see that that carbon that's by your nose is pointing up, right? Directly behind you, which way is the carbon pointing? Directly behind that one. It's pointing down. That's correct. And now if you look at the 2 on each side, if you look down them, they kind of are on the same path, right? You can't see the second one. You can only see the one in front. Does that make sense?
Yes.
This is what the actual ring looks like. And the reason why it does this, the reason why it's not that, is to minimize what?
Energy?
Energy, but what 2 things did we just talk about?
Torsional strain.
Torsional strain and
Angle strain.
angle strain. And that's it. So whenever they ask, why is this a good shape, which is a good test question, it minimizes torsional strain, it minimizes angle strain. So remember, what have I always called chemistry? It's the what of sciences? It's the frat brother. Remember, it always wants to do things the easiest way possible. It always wants to lower the energy to the lowest energy possible. And so this is very important. It's because everything that happens in chemistry can be related to energy. You can think about trying to minimize it, all right? So now when we start drawing these structures and representing them, we've got to keep this in mind. It's to minimize these charges, all right? And I'm going to take a quick look at your PowerPoint because I opened it up. All right. So now when we think about just this regular thing, and I can actually see it here on this one. So okay, I'm gonna try and share screen again to here. How you guys doing, by the way?
Good.
Okay.
I have a lot of lab homework tonight.
You can run it by me later if you want to send me an email or something with it if you have questions. Just don't pull an Ellie.
Did she never send you his PowerPoints?
Well, no, it's ask for help, but don't word it in such a way that's gonna make people notice.
Oh yeah,
Or
and from your university email.
Yeah, on my professional email, yeah, or just send me like a snap or something or Gmail. You know, it's just like.
Yeah, when you said she sent it from her school email, I was like, oh my god.
Yep. Okay, so this question here. So this is something that I actually, let me see if I'm going to scroll up and see if we covered it. So, all right. So basically, when we get into these ring structures, right, which one of these ring structures is going to be the most stable, and it's going to be the 6-membered ring always. And that's because we saw when you were tilting it right, when you do that, you're able to get to the correct 109.5 degree thing. So it doesn't look like it, but you can. All right, so now, you remember how much you guys were sitting there twisting and turning it and trying to get it into the right shape?
Yeah.
You were actually going through all of these shapes. So what you have it in now is something called a chair conformation. These are the lowest energy. You can go from one chair conformation to a half chair, to a twist boat, to another twist boat, to a half chair, to a chair. And basically, it's just you turning stuff. Once you leave the chair conformation, it's not great. The energy goes really high. Right,
So, the lower the energy, the better,
the more stable it is.
the more stable. Okay.
Remember, less energy, less reactive, more stable. Okay, so if you look here, if you notice the carbon on the left is pointing down, and then the carbon up here on the right is pointing up, like they're pointing like this. If you go through this whole thing and you change it, which direction are those carbons pointing now? They flipped, right? Now the one that was on the left side is going upwards when it was going downwards earlier. So here, I'll color code. So that might help. So you see that carbon here on the end? The one I circled, it's pointing down, right? And when you do a chair flip now, this is the same carbon here. Which direction is it pointing now?
So it goes like that?
Yep, now it's pointing up, and that's what a chair flip is that you're changing the angle, right? And if you notice here on the right side, this one on the very far right is pointing up, but now it's pointing down. Does that make sense how the things are changing direction? And this is a chair flip. And in order to do that, like in the normal chemistry world, not just your little plastic thing, you have to go through all of these conformations. So you can do it. It's just, it takes energy.
So basically, like in this going through all of those.
Mm-hmm. So if you try to, you could try to mimic that doing all of those turns and stuff. It would just take practice if you felt so motivated. I could recommend it, but you don't have to do it. Okay. So now, because we can make all of those conformations, which of the following distributed hexane structures is the least stable? Do you guys know?
Number one, because like she said that the methyl groups were like closer together, so then that makes them less stable.
Yep, but there's also something that is exactly right. But this is our chair conformation, right?
Mm-hmm.
These are going to be more stable. These are our boats are less stable. So now you can immediately say, well, it has to be one of the boats if it's the least stable one. And you're right. If you look at the methyl groups, they're pointing in at each other versus here when they're pointing away from each other. And this is the idea of the torsional strain. This is steric strain. When our groups are going to hit each other like that, we have steric hindrance because like our electron clouds are like overlapping. Does that make sense?
Yes.
And so first figure out what the conformation is. If it's a chair, it has the chance of being stable. If it's a boat, there isn't a chance of it being stable. Okay. And so now when you're doing this is how to draw your chair conformations. There's a guy at Harvard that made his grad students practice this for hundreds of these things until you learn how to draw them right.
Really?
Yeah. But basically, this is how you just draw it. So basically, you learn how to do it. There are 3 sets of parallel lines. Right. So if you
Mine look really weird.
I know. Just kind of like draw them all in like one thing, and it's like
Me too.
There's like bow ties.
Just practice until you get it right. And see, now I can draw pretty crude ones. I mean, that's a crude one, but you can get better at it so that it looks better. right? It's just practice. And at every carbon center, like this, you're always going to have an axial bond and an equatorial bond. What that means is you're going to have one bond going straight up or down. That's axial, right? Like an axis. And then you're going to have a bond that's at an angle, equatorial, like, you know, the equator. And it just depends. So for this pink one, which way are the bonds coming together? Are they coming up or are they coming down?
Up.
Yep. So since they're going up, your axial is going to be up. Here, this is going to be down like this, right?
Mm-hmm.
And so they alternate up, down, up, down, up. And if you did the same thing with your equatorial down, equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. So they alternate. Does that make sense? All right. So every carbon has one of these. And so when you think about these with our hydrogen, this is the most stable because we don't have any steric, we don't have any torsional strain, we don't have any angle strain, right? And when we have hydrogens, we don't have any steric strain, meaning that things are not bumping into each other, which is bad. All right. And so now, which represents the chair conformation of the following with both groups axial? Which one of these matches what we drew?
D.
What'd you say?
D.
D? Okay, well, the important thing is here, it doesn't matter. What was the one thing we said when we were drawing structures, you know, like you had to draw them, like they gave you the name? What was the one thing I told you always that had to be true? It doesn't matter how you draw them, you just have to be...
Label them?
That's the second thing. You just combine the first two. You have to be consistent. Consistent.
Yeah.
Consistent. Well, persistent too, right? Don't give up. So which carbons, if I was to number these, have methyl groups on them?
1, 2, and 3.
1 and 3, right? So that means that we have carbon with the methyl, no carbon, a carbon with no methyl, carbon with the methyl. So carbon with the methyl, no. So A is wrong because it doesn't have the correct spacing.
And they're both equatorial also.
Yep. B, they're both axial, right? And it goes carbon with one, carbon without one, carbon with one. So the spacing looks correct, right? There's only one carbon between them right here, which is this carbon. If I look at D, how many carbons are in between my carbons with methyls? 2. So D's wrong. Does that make sense?
Yeah.
So this is the tricky part of you taking what's drawn and then transferring it onto the going from our nice 2D shape into the ring shape. If it's a wedge like that, that means that they're going up. If it's a dash, that means they're going down.
Oh, okay.
Wedge up like this. If it was this dash, it's going down. All right, and then that's an important thing for nomenclature.
Oh, I had a question.
Mm-hmm.
So would equatorial be like more stable?
Mm-hmm.
Okay.
Equatorial is always more stable. The reason for that is that, remember what kind of, we said that we have the torsional strain, that's from the ring, right? We have the angle strain, and that's from, if you're not at the ideal like Vesper angle. Do you remember what type of strain I said comes from that when your groups are too close together? Starts with an S. Steric.
Okay.
Steric strain. And this is when your groups are too close together. So if you look at B here, right, those methyl groups are both pointing up. And what's coming off of those methyl groups?
That's a good question. Is it the axial?
Hydrogens are coming off of those carbons.
Oh.
Like this. So this is what's really happening here now. You have these hydrogens that are just hitting each other. Can you see them? Oh, now they're standing up. So like you can imagine if they're like this and you've got that steric hindrance, and that's not ideal.
Okay. It's steric the same as gouge? Is it gouge?
So steric hindrance is what that's called. A gouge is a type of steric hindrance.
Okay.
All right. So now ring flips. Remember how we talked about we can ring flip? Remember how if it was pointing up, now it's pointing down kind of thing?
Mm-hmm.
Here's the important thing. If you have a ring flip and you see here, what is the position of the X before the ring flip?
Axial.
Axial. And is it axial up or axial down?
Up.
Okay, so now after the ring flip, what is the directionality of my group?
Equatorial.
It's now equatorial. So I went from axial to equatorial. Is it equatorial up, equatorial down? Up. The directionality will never change. It'll always be up if it starts up. Okay. You will just alternate axial, equatorial.
Oh.
But you will never be going like from up to down.
Okay.
Does that make sense?
Yeah.
Oh, I thought, okay, so when we did that problem right next to that slide, I thought that that the axial up would go axial down.
We alternate between axial and equatorial when we do a chair flip. Okay. It's still, so if you see here, I've drawn a 6-membered ring with a group, right? And you see how it's pointing up? This ring represents this one and this one, right? It has to represent both. That's why it doesn't alternate between up or down. It's always pointing up. It's just, is it doing axial up or equatorial up?
Okay.
Does that make sense?
Yeah.
Okay, so if we look at the question next to it, when we do a chair flip, that OH, what is its position right now, Gwen? Before we do the ring flip?
Axial up.
So when we do the ring flip, is it going to still be going up?
Yes.
Is it going to be axial or is it going to change to equatorial?
Equatorial.
Correct. And so now what happens is that OH, right, is going to be up and equatorial. Oh, how if I, this one here, right, that's going up and that's equatorial, right? What about our methanol? Or sorry, not our methanol, our methyl group. This is up and equatorial, but now it's going to be up and axial, right? Like this. D, right, looks correct. What's wrong with D? It has the same groups.
They swapped places.
Yep, they swapped places, right? And remember I said it doesn't matter how you do this, you just have to be consistent. So what I'm going to show you here before we finish up is that if I call that carbon 1, carbon 2, 3, right? One's with the OH. 1, 2, 3. And so this arrow is going like this. This arrow is going like that. So you see how I count. One's going clockwise. The other one is going counterclockwise if I number. Does that make sense?
Yeah. So in this case, it would, if you have like OH and the methyl group, they would all have to like move in the same direction. They can't like.
See, what I was saying is if I number them, right? So if I, in my original drawing, if I call the carbon with the OH 1, and then I call the carbon with the methyl 2, then this would be 3, 4, 5, 6, like that. Which direction is my arrow, clockwise or counterclockwise? Clockwise. If I do that here, 1, 2, 3, 4, 5, 6, which way is it now? Counterclockwise. So I wasn't consistent. It still has to follow the same naming conventions.
Gotcha.
Does that make sense? Okay. About a minute left. I'm going to wrap up there. So basically the idea, what we were talking about last week, you just still have to be consistent with everything, right? Your numbering, your everything else like that. And as long as you're consistent, everything will work out. So I can host another one of these. Is there a day of the weekend or weekend you would prefer? It is a 3-day weekend coming up. So we're going to be snowboarding.
Yeah, I'm snowboarding on Sunday.
How about I do one on Saturday and you guys are free to join? If not, I will post it. If you have questions like from homework or stuff, send it to me and I can work through them on this video.
Okay.
Okay, the homework's due Sunday night, so we
Okay.
can go
Yep.
through it and ask questions.
Yep. Take care, guys. I hope you have a good night. Congratulations on your tests. I know you guys kicked ass.
Thank
Yep,
you.
you'll do
Thank
better
you.
next time if you didn't do it this time.
Bye.
Bye.
Thank you.
Oh, you're welcome.